only identifying what forces act externally, but where they act. It's important to put them in the right place. So also where they act. If you're computing the net force, you don't care where they act, but it's going to be really important for torque. Okay. So that's actually it. Those are the three forces that act. There are no more. Now you might be asking, isn't there a normal force from the plank on each person? Yes. Is there a normal force from this plank on this person? Yes, but why am I not including that? It's internal. It's between the plank and the person. You might say there's a force on the person from the plank, also vice versa, Newton's third law. There's a force on the plank from the person. Those are internal. Don't care about those. These are all forces coming from outside. Two forces of gravity and one support force. Okay? So make sure you understand why those are the only three forces to include. If you include the wrong forces to start with, you're tanked from the beginning. Okay? All right, so first of all, I can certainly balance the forces. Notice here that there is no x and y direction. There is just simply a y direction. And what you're going to get from that, net force y equals 0. Let me bore you, not bore you. The answer, of course, hopefully this is something you can work out. The normal force has to support the collective weight of the system, right? That's what makes sure that the thing doesn't fall down or anything else, is making sure that the seesaw support can hold up the entire weight. I didn't ask for that, but that would have been an excellent second variable to ask for, right? So where do you balance it, and how much force does the support need to provide, right? It's classic two equations, two unknowns. Of course, just because I can ask you for two unknowns doesn't mean I always will ask you for two unknowns. The other unknown, where, well, that was not going to come from the force equation, right? There's no mention in the force equations about where things are, so it's going to have to come out of torque, okay? So let's figure this out. The net torque, well, we have three possible candidates: torque 1 of gravity, second torque from gravity, torque of the normal force, and those all have to add up to 0 for this system to stay balanced. All right? So this is where, for at least this example, we can take advantage of an intuitive pivot so that we don't have to worry about pivot issues for this problem. The pivot where I'm going to pick is obviously going to be at the seesaw pivot. And one of the things I noticed right away is that the normal force acts right there. The normal force acts at the hinge. So how much leverage does it have? It doesn't have any leverage against the pivot. It's like trying to open a door by pushing on the hinge. So right away, this torque can be ignored because that force has no leverage. So the reason why the net torque can be 0 is because the other two torques, which won't be 0 on their own, are going to have to fight and cancel. So one of the things I might actually want to do, just to help myself out, is do sort of like a rotational version of a free body diagram. So I might want to redraw this thing, put in the pivot. I'm not going to draw the normal force because I've already decided that it's not relevant. And then draw in the two forces that will matter. So force of gravity 1, which is kind of here, and force of gravity 2, which is kind of here. So let's take a look. First of all, let me remind you of the torque formula. We're going to have to figure out each of those things for the purposes of computing a torque. Let me start with the angle. Angle is really pretty straightforward. Draw a radial line through each force application point. Measure the angle. and I find that the angle is 90 in both cases. Sine of 90 is 1. And that, of course, signifies that these forces are entirely tangential, right? So both of these forces are perfectly tangential around the pivot. But notice that they both want the system to rotate in opposite directions, right? This torque, is this torque plus or minus? It's plus. Now, again, you might look at this and go, oh, it's pointed down, but that's not what it's about rotationally. It's all about counterclockwise and clockwise. So this is plus because it's counterclockwise. And the other force, which I should note, is pointing exactly in the same direction. Both poles of gravity are downward. But because it's on the opposite side of the pivot, that force would tend to drive the rotation in the negative or clockwise manner. Right? So if you have a seesaw, if the person on one side gets off, it'll rotate clockwise. If the person on the other side gets off, it'll rotate counterclockwise, right? So even though both forces act downward, they act at opposite sides of the pivot, so they drive the torques oppositely, and we're trying to figure out how is it that they add to 0. Well, the forces are not equal. Oh, I mislabeled this as force of gravity 2. Sorry about that. The forces aren't equal. And of course, if you had to weigh the same as a little kid, then you can never seesaw with them, right? If it was about the forces balancing, you always weigh more than they do. But luckily in a rotational system, it's not about the forces being the same, it's about the torques being the same. And so if you have more force, you can compensate with less leverage. So we also need to account for this distance, R1, and this distance, R2. Those are distances from the pivot. So let's go ahead and summarize what we have here. We have that this torque was the plus 1, R1, F1. This torque was the negative 1. This torque was 0 all by itself, and those all have to cancel. And we go over here, solving. I'll go ahead and also put in force of gravity is mg. And there we have it. You can get this system to balance out by making sure that if you have more weight, your mg is larger, your leverage is smaller. Okay? In fact, we can go ahead and just cancel off the g's and realize that it's about having the product of your mass and leverage be the same as the other person on the other side. So if you have more mass, as long as you have less leverage, your torques might still balance. So I should point out we have 3 out of these 4 numbers. We have R1. How much is R1? What's the leverage of this force against this pivot? 3. So that's 3 meters. The mass is 2 kilograms. We're trying to find R2, and knowing that mass 2 is 4 kilograms. So this is where we can very easily see that since the mass is twice as much, the R2 is half as much. So after much ado, we get R2 is 1.5 meters. So you can see that the torque considerations do allow us to work in distances, so where forces need to be applied. Okay? Are there any questions on this example? Okay, so hopefully you kind of see the strategy here. We've identified a group of objects, in this case seesaw plank and two masses. Even though the seesaw plank did not have any mass of its own, of course the seesaw plank is where the normal force is applied. We identified external forces only. There were 3. We made it a point to not only identify them, but have them act in the right places, because that's going to definitely affect your leverages. We plugged in Fnet, something into the net force equations. This would have formed a perfectly good second variable to ask for. But in this case, the one thing that I asked for came out of the torque equation, which is totally expected because it involves something about wear, and that will never come out of the force alone. Okay, so if there are no further questions on that, let me see how far in the next 10 minutes I can get on doing a more complex static equilibrium problem. So my example now is like this. I have a diving board, and I have a person just sitting on the end contemplating jumping, okay? So we don't want any motion here yet. We just want static equilibrium, okay? I'm going to say that the mass of the person is 50 kilograms. I think that's, yeah. And then the mass of the diving board, mass of the plank or whatever, is again negligible. I should mention, by the way, that if it did have mass, it's not the end of the world. But let me leave it massless for now just to expedite. So what that actually does, it puts the center of mass of the system way over here. It basically is synonymous with this person's center of mass. Of course, this is not realistic. If you had a really heavy person and a really light diving board, the center of mass would still be not right on top of the person. It'd be somewhere skewed far toward the person, but it wouldn't be right on top of the person. But here we have that the force of gravity on this entire system pulls way over here. So in the center of mass balance method, if we wanted to balance this with a single support force, we'd have to put it, strangely, on the far right end. And you'd have to just imagine this like 0 kilogram plank just hovering there, sticking out. Okay. In reality, of course, the center of mass of a heavy person and a light board would be somewhere over here, and that's where we have to balance it with a single support force. But this is where the limitations of the whole single support force comes in the first place. You don't want to put a support over here. You want the end of the diving board to be nice and loose so you can spring up and down on it when you're actually ready to stop contemplating your jump and jump in, okay? So you don't want to support the system with a at the center of mass. So rather than having a single support force at the center of mass, we are going to use multiple forces. And if you are willing to use multiple forces, you do not need to put them at the center of mass at all. So to give you an example, if I wanted to balance this eraser with a single force, I'd have to put it right at the center of mass, right? But I can actually support this eraser by putting an upward force way over here on one side, but then I also have to hold this down. So I'm doing it with 2 forces. So this one holds it up, and then this one keeps the end from flipping up. So if I let go of it, it would go like that. So I have 2 forces far to one side, one that's up and one that's down. Okay? So there, you can see that the center of mass method, which got us out of, or we could use for doing our last example, now that's not going to work at all. I'm going to put one force support here and one support here. So what we have, if this is our system, the diving board plus the person, we have that this support, which I'll label, I guess I'll label these A and B. The job of support B is to hold the whole system up. But since that is far to the left of where the center of mass is, we also need to apply a second force which prevents the end from flipping upward. Okay? Now, if you've ever seen a diving board, there's obviously not some big claw coming up and over the end, but that is the job of the support at the far end. It's not to keep the system from falling down, it's that when someone's jumping hard down on the other end, down over here, that this doesn't go up. So this holds it down. And I've characterized them both as normal forces by putting surfaces there that don't want to get smushed. Okay? So those are my objects of interest. I've grouped my system is the man plus the board. I've identified external forces, including where they act. I don't include the internal force between the diver and the board. And I can go to my force strategy. Oh, I should tell you what I'm asking for. How about that? I want to find out both of these forces. How big are they? How big do they have to be for this thing to not fall down? And then I guess I also need to tell you a little bit about the geometry. Let's say the whole thing is 5 meters long. And let's say that the support A is at the end and support B is only 2 meters to the right. So you can clearly see that all the mass is on the right end and the two forces that are in support are to the left of the middle. So you can support something not at the center of mass if you are willing to use more than one support. Okay? So you can hold something up not at the center of mass by using multiple forces. All right. So first of all, let's knock out the easy thing. Let's knock out the force equation. So F net, well, let's say that this is the plus y direction. F net y equals 0. So in order for the center of mass of the system to stay put, all the vertical forces have to balance. So I have an upward force from B and 2 downward forces from the other support and gravity. Looks like that. And if you group that, you'll end up getting this, which you may, hopefully, at this point in the course, just be able to write down, right? The size of the upward force and the size of the downward forces have to be equal. So this alone is not going to get me very far. I can certainly put in my mass is 50 and get my weight of my diver is 490 newtons. But this just sets up a relationship between these two forces, saying that one force has to exceed the other by 490. There is no way that you can get two unknowns out of one equation, right? Can't squeeze blood from a stone, can't get two unknowns out of one equation, okay? So this is where you get your two equations, two unknowns, a little bit more intertwined, right? We're going to get a second equation from torque, and we're going to solve simultaneously, right? I guess before I even do that, I should mention, what would you do if the diving board itself had mass? I mean, what if it wasn't massless? It wouldn't really be very hard at all. you just include an extra pull of gravity for that. And presuming that it is a diving board that's reasonably uniform, you'd probably take it to pull right in the middle, right? So then you'd have 4 forces to contend with instead of 3. No big deal, okay? So if I gave you the same problem, but the diving board itself had mass, that should not be a huge curveball for you. Now, our second equation is going to come from torque, but here's the problem. This is not a seesaw. This is not something that is designed to tip, where it has an obvious pivot where it usually tilts, even though it may not be tilting at the moment. This is not supposed to be a system that rotates in any way, and so the question is, what do you use as the pivot? So we have some issues here with what do we use as the pivot? Well, I'm not going to have time to tell you about that too much today, but I do want to tell you that if a system doesn't rotate, if the net torque is 0, it must be net torque of 0 around any pivot. When something is not rotating, it's not a matter of perspective, okay? All observers think it's not rotating. So no matter what pivot you used, you should agree that there is no rotation around that pivot. So it turns out that we have a wide latitude in choosing a pivot that we feel like choosing to make our calculation easy. It actually is also true for the seesaw problem, okay? If you want, you can use some crazy pivot there that isn't intuitive. After we do this example, I'd recommend that you go try it. Try solving the seesaw problem with a different pivot. So if the net torque is 0 on any pivot, well, the next thing we need to discuss is what pivot do you choose to make your calculation as short and easy as possible rather than as long and annoying as possible. Okay? So let's call it a day there. I'll pick this example up next time.